Okay, so lab 3 is all about getting the LCD screen working. And I have them right here. So here is the LCD screen. So you can see it has these 4 wires right here. If we flip it over, we can see what they correspond to. We can see VCC, ground, clock, and data. So what interface is this? It's I2C. Yep, exactly like you did in lab 2. And now you just have to use this wire. And notice that you will have to go and plug these wires into your breadboard and get them all connected up. And then on your microcontroller, you can see that there are dedicated pins for the I2C line. So that is how you connect the LCD. And then you will configure the LCD and you can write things out using the library that was provided to you. I explained most of this last class, which I can post the lecture for very quickly. What I will now talk about today is PWM. That is another functionality that you will need to take advantage of for the for this project. Now, PWM is actually baked into the LCD controller itself, so I don't think you actually have to do like PWM functionality on the ESP itself, but it's still important to know. I think there may be a lab that uses PWM later. So okay, cool. So we'll talk about that. Has anyone heard of PWM before? So maybe just PWM. Okay, yeah. Maybe you've done an Arduino project and you've done something called analog write. Okay, so usually when we think of like microcontrollers and digital circuits, usually we just think of things being like on and off, like either just 0 volts or 5 volts or 0 volts and 1 volt. But if on some microcontrollers, in the Arduino IDE, Arduino stack, you'll see that you have like an analog write functionality where you can actually write like analog values to a pin. But what actually happens is when you write to a pin, it actually only has the functionality of being like on or off. There is no like analog value. You can't say put it at like exactly like 2.5 volts now or put it at half a volt. Instead, what you have is PWM, which stands for pulse width modulation. And the idea with pulse width modulation is that instead of having like here you can see this like analog signal, this red signal right here, like if this is our desired output, well, unfortunately we can't actually create this red output, but what we can do is maybe we can provide this blue output. So here, like if this is some sort of audio signal, maybe we are trying to drive some sort of speaker, and in order to do that, we would have to instead send like pulses with a certain width, and we would say like, okay, so maybe like this pulse is sent for like 10% of like this time, and this pulse is sent for another 10%, and then this one is like really skinny, so this is like 5% of the time. And that is how actually like the analog write pins often work on microcontrollers. It's actually there is not an analog, like you can't get this red output. Instead, you just turn on and off the pin at like a certain rate. Okay, why is this potentially actually a benefit? Like you may think like, oh man, that kind of stinks. Like I wish we could get like perfectly like these like analog values here. Why may it actually be beneficial to have your microcontroller only output like either voltage high or voltage low? Why is this okay? Yeah?
It takes less power than providing like between 1 and 5 volts.
Sure, actually, so it does take less power because most likely if you had to output some sort of like analog signal like this, you would need to create some sort of like resistor network in order to properly like divide the voltages out. So actually, it would take a little less power. But that's probably not the main reason. What is another possible reason for why we only want to have voltage high and voltage low? Okay. Yeah?
It's a digital system.
Sure, it's a digital system. So our peripherals, for the most part, also only expect voltage high, voltage low. Even like LEDs. Like LEDs, they actually are configured to work most well when you feed them a like exact voltage and an exact current. And if you now fold them like half the voltage, what's going to happen is it probably just won't turn on at all. Or if you give it like half the current, maybe it just won't turn on. If you give it twice the current, it'll burn out. Like LEDs are kind of expect like a very particular amount of voltage and current passing through them. And that is good because what we can do is like if we want to now dim an LED, well maybe instead of just giving it like half of the voltage to like dim the LED, instead what we could do is make the LED just flash. Maybe we can make it turn on for like 1 millisecond and then off for 1 millisecond and on for 1 millisecond, off for 1 millisecond. And that would now mean that the LED would appear like half as bright because it's actually only on half the time. Yeah. And that is like actually how you dim an LED. I don't know if anyone has seen like cars that have LED headlights on, and you may notice like if you're looking out of the corner of your eye or something, you may see that it actually almost looks like it's flashing. Has anyone seen that? Yeah, where like car LEDs will look like they're flashing. This is the exact reason. It's because LEDs only really operate at a very specific current. And so in order to dim the headlight, in order to not have it blind people, instead you just decrease the amount of time that you're actually spending like on as you're flashing it. Yeah. Okay. I'm gonna skip ahead a bit. Okay. Yeah. Cool. So this is generally the way that PWM is implemented. So here, I'll pull this up over here. So here you can see that this is called a 50% duty cycle because the signal is like voltage high half the time, voltage low half the time. This would be a 75% duty cycle because in the blinking phase, you can see it's actually on for 75% of the time. And then in a 25% duty cycle, it's only on for 25% of the time. Okay, question. So which one of these three would have the brightest LED if you were to plug this signal into an LED? Probably the 75. Yeah. What would be the dimmest? Okay, 25. Yeah. Okay. Question for you now. Let's assume maybe these are running each at 1 kilohertz, 1,000 times per second. Now, let's say I've doubled the frequency. Okay, so I doubled the frequency. Will that now mean that the LED will run brighter or less bright if I double the frequency? Okay. I think we'll actually say the exact same, right? Because it's only on for 50% of the time. It just means it's blinking faster. Yeah. Okay, there we go. The way that PWM is implemented, actually all microcontrollers have built-in timers in them. And we can take advantage of these timers in order to be like very fine-grained with how specific we need that duty cycle. Because maybe actually we're controlling like a robot arm and we need to move with like micron accuracy, and we like really need to make sure that that it moves the exact same amount every time or something. And so therefore, you wouldn't just want to write like C code that's like, like sleep for this amount of time and like move it for this amount of time. Yeah. But let's actually look at what that kind of code would look like. Do I have that? Oh, good. Okay. Cool. So this is a kind of a naive approach of implementing pulse width modulation. Okay. Go and absorb this code for a second. And what I want you to do now is tell me the frequency. Go and maybe write it down or take notes on it. What is the frequency of this, and what is the duty cycle of this? Okay, begin. So duty cycle, let's do duty cycle first. So we can see that it is turned, is this on or off? This is off, so it's turned off for 10 milliseconds. Then it is turned back on for 10 milliseconds. So therefore, what percent of the time is the LED on? Yeah, okay, 50% of the time. So this would be a 50% duty cycle. Okay. What is now the period of this oscillation? Yeah, so the period is 20 milliseconds. So we just take the amount of time that it takes to run, and that would be about 20 milliseconds. Then how do we convert 20 milliseconds into frequency? What would the frequency be? Yeah, so it'd be 1 over 20 milliseconds, which I believe is 50 hertz. Is that right? Okay, so this would be a 50 hertz oscillation at 50% duty cycle. Okay, if we wanted to change this now to a 20% duty cycle and maybe keep the same frequency. How would we now do that? Okay, think about it for a second. Maybe write down the answer. Tell the person next to you. So we want the same frequency, but now 20% duty cycle. Okay, so we probably need both sleep functions to take the same amount of time as these two. So what would the total amount of time be? The total amount would still need to be 20. So that would mean if we want it to be split up into, like, I guess, 80% and 20%. So what's 80% of 20? 16. Yeah. And then finally 4. So it would be probably off for 16 and then on for 4 for a 20% duty cycle. Okay. Great. Why now, so I kind of briefly mentioned it, so why now should you not actually write code like this to generate a PWM signal? This seems pretty easy, but yeah, why should we actually not write code like this? Well, I'll cut a little bit ahead, but I'll tell you that this is actually not going to run perfectly at 50 hertz. Like, the timing is not going to be quite exact. And that's because, like, actually it takes some amount of time to run each one of these functions. Like, setting the GPIO level, well, it's kind of like the CPU is going to branch into this instruction, or branch into this function, and then it's going to look at all the if statements in that, and it's going to write to, like, internal registers, and then, great, okay, then it runs that. Then it goes and runs this function next, and it's going to take a while. And so actually, you're not going to quite have 50 hertz. Maybe it'll be closer to, like, 48 hertz or something, or like 49 hertz. And yeah, like I said, if you're coding like a robot arm that needs micron level precision, that whatever 2% error is not good enough. Another thing, operating systems. They really love to just stop running user code. What will happen is, like, if you write a program and the operating system realizes, like, actually, like, I have a bunch of things running right now, like I'm running a bunch of different programs and things, what it can absolutely do is it can just choose to stop running something for a little bit and then go run something else. This, like, happens all the time on computers. Like, if you have a bunch of, like, tabs open on Chrome, and now your operating system will context switch out of one application. It'll just completely stop running it for potentially, like, a few milliseconds, like probably nothing long enough for you to really even notice. But yeah, like I said, if you're controlling a robot arm, or if you're controlling the brakes to a car or something, or something that's extremely timing critical, then you wouldn't actually want to write code this way. Okay. What instead you would do is you would take advantage of the internal hardware that goes into ESPs. Okay, anyone remember Verilog? Verilog. Okay, anyone who in here has written some sort of, like, counter in Verilog? Okay, yeah, good. That is actually exactly what an ESP, like PWM, like internal hardware is you have some timer, and it's just a counter, and it will just count up from 0 to some sort of reset value. It'll just count up, and then it'll go and reset, and, like, count up, and reset, and count up. And then what you do is, inside of your PWM channel that you can configure, is you just set a threshold value. And you say, once I have gone past a certain count value, maybe the counter will count from 0 to 10. And you say, okay, once you reach the value 8, then now output that as a logic 1. Okay, let me write that out. So if we have a timer that resets at 10, so maybe it counts from 0 to 9. And let's say that this is running at, I don't know, 1 kilohertz, okay? So the clock, internal clock maybe is running at 1 kilohertz. Probably would be closer like 1 megahertz, let's call it 1 kilohertz. So it counts from 0 to 9. And then let's say that the PWM high PWM is high when counter is greater than equal to 8. Okay, so this would be the sort of configurations that you would put into your timer. You would put in like this right here. So I'll go and put this in like brackets. So this would be a configuration. So you say, okay, this is at what point we want PWM to be outputted. Then you would also have a configuration right here that would say like when does the timer actually go and reset. Yeah. Okay, cool. Now the question is, okay, so what would now the clock frequency, sorry, what would the frequency be of this PWM signal? What would the frequency be? So it counts from 0 to 9. So that's going to be 10 like oscillations inside of your counter. So I believe the frequency would be what? What was it? I think it would be 100 hertz. Let's see, it's 100 hertz. Yep. But the duty cycle would be what? Duty cycle would be what? 20%. 20%, exactly. Cool. Okay. Now, let's say I want to, let's say I have a internal clock of, I don't know, 10 megahertz. And let's say this counter, like the max reset is, whatever, 2 to the 16. So like a very large value. So the question now is, how can we create a signal that has a frequency of 100 kilohertz and maybe have a duty cycle of 60? Okay, go and do that. So create a frequency of 100 kilohertz. Cycle of 60%. Okay. This will be the last quick math question at the moment, and then we'll move on to some code. Okay, go and do this. Actually, I'm going to change it. I'm going to say, maybe not. Let's say 50 kilohertz. Yeah. Okay, what should our timer's reset value be? So the maximum reset is this very large value. So our current, like our counter is incrementing at at 10 megahertz. So the question now is like, how do we downsample this into now, so that it now becomes 50 kilohertz? What do we like divide it by? Okay, yeah? 199, I think around like 200, yeah, sure. So I think we would have a reset value of 200. And so now when we divide now 100 megahertz by 200, we would now get a 50 kilohertz signal. And so now, what would the threshold value be in order to say like anything above that threshold would now be a voltage 1, anything below that threshold would be a voltage 0? What would the threshold value be? We can also think it's just 60% of like 200. So what is 60% of 200? Yeah, so this would be 120. So I guess we would say like we want it to be on for 120% of the time, or sorry, 120 cycles, and we want it to be off for 80. So maybe the threshold is 80. Threshold is 80. On for 120. There we go. Excellent. You're masters of PWM now. PWM. Good. Any questions on this? Sure. Makes sense. Good. Cool. The ESP, yeah, has this internal hardware that you can just use at any time. You can create a timer, and you can create like this threshold, And you can then, you can set your own frequency, and you can set your own duty cycle, and you can now turn on LEDs at whatever rate you want, at whatever brightness you want. The higher the frequency, the less easy it is for you to see what's going on, but also the more power it's going to take, I believe. So it's a trade-off. Okay, let me see. Is there any other important slides in here? Yeah, he's good. Good. Sure. Yeah, cool. Okay, I think we'll switch to some code now. So, all good? Yeah. Here is ESP IDF. So I actually found, by just searching in this repo, I found a PWM example. And what I can do is I can just search for PWM. And VS Code, I don't know how many of you use this feature, but I love this feature. You can press Control-Shift-F, and you can actually search every single file in the entire directory structure. Anyone use this? Control-Shift-F? Okay, you use this if you have not already used this. Yeah, it's great. On macOS, it's Command-Shift-F. Yeah, and you can search all the files. You can say only show me, here I'll zoom in a hair. So you only show me .c files, and only show me things from the examples directory, and also hide anything that is inside of build, and hide anything that is inside of components. And so what I can do is I can scroll around, probably not going to use Bluetooth, analog comparator, probably not, I2C, no. Oh, LEDC, so LEDs, common use case of PWM. For example, the LCD backlight, the reason why there is PWM inside of this is, the reason why there's PWM in the LCD is for the backlight LED, so in order to turn on the backlight on the screen so you can actually see what's going on. But you don't want it to be on full blast, so you can actually control the brightness of the screen using PWM. So okay, so here we go, good stuff. So here is the example PWM project that ESP provided. And now we can take a quick look at this. And now, depending on your microcontroller that you're on, some microcontrollers, the top-level API that is used to configure the PWM, sometimes it will have a slightly different interface. On the ESP32, it's actually even more simple than what I showed you, because now instead of having to specify the timer reset value and specifying the threshold value, instead what you can do is actually just set a frequency directly inside. So here, you can see, so here's the init parameters right here, and right here we can actually put in the frequency, and if we scroll up, we can actually see it's being set to 4,000 right here. So this denotes 4 kilohertz. If we want, we can change this to any value we want. We can change this to 60 hertz or something, or some other value. I'll leave it at 4 kilohertz. Here we can set the duty cycle, and it looks like actually, for some reason, the ESP interface has chosen that 4096 is the value of a 50% duty cycle. Okay, so they've just chosen that, and we just have to kind of just use that. It might be because we are setting this timer to the 13-bit mode. I'm not exactly sure why they've chosen to set it this way. I don't know if the ESP only supports this 13-bit mode. But importantly, we can see, so 4096, so this means a duty cycle of 50%. If we now want this to be a duty cycle of 25%, then we can just multiply, or we can just divide this by 2. So this would now give us a duty cycle of 20%, or if we want to have a duty cycle of lower, we could divide it by a bigger number. Okay, let's go and just run this example. And here you can see I changed the pin number to pin number 7, which is in fact one of the LEDs on our board. So I'm going to now flash the board, and hopefully this works. And it is still flashing. One sec. There we go. Okay, so this right here, nice LED, it is at a 50% duty cycle. Okay, let's see what happens if I change this now to a much lower duty cycle. Maybe I'll change it to a 10% duty cycle. So I just decreased the threshold value quite a bit, and now it's reflashing. Memorize what that brightness was ahead of time. Let's see, hopefully this is going to be dimmer now. Okay, it's almost done. Okay, does that look dimmer? It looks a little bit dimmer. Okay, great. Let's go and turn it just on a little bit brighter. So I'll make this now the, I don't know. Okay, in theory, this should be brighter. So I just increased the threshold value even higher now. Okay, there we go. See, it's brighter. Yeah, I'll show you what the code that I wrote looks like. So you can see I multiplied this 4096 by just 1.9. So you can see it's like almost, yeah, it's almost a like full 100% duty cycle, but yeah, 1.9. Good stuff. Okay, yeah, question?
What if we set it to like a very high number? Would the LED burn out?
Oh, sure. So yeah, the whole point of PWM is that all that it is, it's just like voltage low and voltage high. And so the LED will never burn out because the maximum like current that we're putting through it is the like actual rated current for the LED. Like we are unable to increase the, or we're unable to increase the like duty cycle past 100% because at that point it would just be feeding in like the maximum allowed current at all time, as opposed to the maximum allowed current for just like a short little period. Yeah. However, you actually can burn out LEDs, if you do set your duty cycle too high, if the LED is like extremely bright and you don't have good cooling on it. Like, car headlight LEDs can get like extremely hot. Like we kind of think of LEDs as being like very power efficient, but actually like you can get really bright LEDs that will burn so hot that they'll burn themselves out. In that case, maybe you would want to lower your duty cycle, but in this LED, that's not the case. Yeah, sure, cool. Any other questions on this? Making sense? It's all good? Yeah, PWM, super useful. Common use cases of it, LEDs, motor controllers. Yeah, because a big thing with motor controllers is you want your motor to be running at like the optimal speed and everything. You want it to be running in optimal conditions for like a very well-known amount of time, because if you are running at like an undefined voltage because you want it to run like a little bit slower, then your motor may have more error in its movement. Versus if you're using a PWM signal, you get a lot more precision in how you move motors.
If we were to turn on the frequency a lot, would we be able to see?
We actually would, yeah. Okay, question. So actually, okay, let's see what happens. I don't know how low we can turn down the frequency. I think the lowest the frequency might go is still like 60 hertz or something. But I don't know. We can test it, or let's see. It might tell us what the frequency is, maximum. Anyone want to Google what the lowest frequency of a ESP32 is for the PWM? Can quickly see.
I think you can go down to 10 hertz.
10 hertz? Okay, let's try it. So 10 hertz. Okay. I did not test. Oh, you're not going to believe this. Yeah. Wow. Cool. So you can actually see it blinking, I guess, 10 times per second. So actually, let's go and lower the duty cycle, and now we should see that it's blinking at the same rate, but just like shorter bursts. Okay, so I just set it to a much lower frequency, much lower duty cycle. You can see now 5% of 50%. And still programming, and there we go. So you can see it's still blinking at the same frequency, but it appears dimmer. It's also, I think it's just an issue with the camera. It's not really able to pick it up well. But if I look at it, it does look like it's a shorter pulse. Okay. If I now set it to something really high, let's say 1.95. There we go. Now I'm setting it to very close to 100%. you can just barely see, if I look at it in person, that it's like turning off with just a hair. Let's see, I'll write this down. Yeah. Yeah, good. Okay. Can you see? There you go. Cool. Yeah, cool. Good stuff. PWM. I think I went a little bit faster than I usually do when I teach this lecture. I don't think I really missed anything though. Any questions on anything? I guess we could talk about more parts of Lab 3, or we could move on to Lab 4 if you want. Yeah, question?
Yeah, so when you turn down the frequency, it's
Yes.
just like a byproduct of that, it's going to be brighter too, right?
When you turn, right.
Because of like the percent of the duty percent or whatever.
So
It'll be longer.
the question was, when you turn down the frequency, will it be brighter in the bright part? And the answer is no, because actually the LED will blink so fast, like it's able to respond so quickly that it's actually, like, even though it's only bright for like maybe potentially like a microsecond or maybe like a millisecond, it's so bright, it's such a fast response that if you had like a slow-mo camera, you would actually see it turn on for the full brightness and then off like fully dim and then on for the full brightness. So you would actually see, if you were to slow it down and like match the frequency depending with your camera, that the bright part of when it's on would be bright no matter what frequency you're running it at. Yeah. You can ponder that. There is like a little bit of response time, like when you turn on the LED, maybe it takes maybe a microsecond in order to actually ramp up and become like a bright LED, but our eyes just aren't able to perceive like how fast it's blinking. So it actually just appears dimmer. Yeah. Okay.
Well then how come for like changing the duty percent can make it dimmer? Because isn't it?
Well, it's just on for less of the time. So to our eyes, it looks like it is dimmer, but it's actually just on for less of the time. Like it looked to us humans who have like flawed eyeballs, it looks like it's dimmer, but it's actually not dimmer. It's actually flashing. Yeah. If you had like a slow-mo camera, you would actually see it like turning on full brightness and off. Yeah. Okay, well, I guess that's probably good enough for today, unless anyone has some questions. I forgot to post a quiz over the weekend, so there's just going to be a longer quiz that is due next Monday. It's going to involve PWM and also a little bit of I2C stuff, so look forward to that. And then we will return on Wednesday, where we will continue talking about things that you need for Lab 3 and for Lab 4. Okay, I'll see you on Wednesday.